Hi and welcome to another edition of Ordinary Differential Equations. Today we are going to talk about interval of existence of an equation. Let's go ahead and take a look at an example of this problem. So interval of existence is a topic we looked at before. If you remember when we did this in the case of separation of variables, some of the questions there were asking for interval of existence. The process there was rather complicated because it was a nonlinear equation we were looking at. And now we want to say a rather good news that if your equation is a linear equation, you can find the interval of existence rather easily. So we are going to look at a kind of an equation that you remember was a linear one. Y prime is equal to some function times y plus some other function of time. And an initial condition is specified. The pair of these things are referred to as the initial value problem or an IVP. The theorem that we are going to state, we are not going to prove it. The proof is delegated typically to a more advanced class or real analysis class. It says that if P and Q are continuous on some interval I that contains your initial condition, then you are guaranteed that there would be a unique solution that's going to extend at least as far as I. And that's where the solution is going to be continuously differentiable. So we are going to try to make sense of this in the context of some examples and see how it works for us. So here's I have an example for you. Y prime is equal to y times tangent of t plus t minus 1 over sine of t. We want to find interval of existence. The good news is that we are not going to try to solve this equation. It's going to be rather difficult to solve this because the integration problems that we are going to come across are either going to be difficult or perhaps impossible with the aid of functions we already have at our disposal. That's not the plan of attack. The plan is just look at the ingredients of the equation and tell what the interval is going to be. Well, you might ask yourself, why should there be any limitation to the solution anyway? Why wouldn't the solution exist all the way from minus infinity to plus infinity? It's rather obvious by looking at this as to what the issue is. What is causing the problem or the solution of this problem to have a limited domain of existence? Let me ask you to think about it for a minute and see what are the red flags in the equation itself that tells you you should suspect something is going to happen. Okay, so it's one of the typical spots for this course. We are going to signal to you that you're going to think for yourself and see what is about to happen. Okay, so you pause this thing and look at the equation and let yourself know as to the picture wasn't letting me to go back. Interesting. What do you think the issue is? Well, if you zeroed in on this sine of t in the denominator, you're on the right track. This sign in the denominator can easily become 0, and if it becomes 0, you're dividing by 0, the quantity becomes infinity. It's likely to push y and y prime to keep pace with that, and they will go to infinity as well. So the function itself is going to rupture and become discontinuous, and there is going to be a stop to its domain of existence. So we clearly see that sine of t in this denominator is a red flag. How about tangent of t? Does tangent of t have a red flag built in? Again, you want to stop and tell me if there are issues with respect to tangent of t. Okay, you stop that. You don't want to get stuck with that picture. That was misbehaving. So let's see. The problem is going to ask us find the interval of existence of the solution of this ODE, and is giving us a variety of scenarios for where the initial condition happens to be. The first one says y of 1 is at 3. The second one says no, y of 1 is 5. Part C says what if y of 5 was 7, and part D says what if y of 10 was minus 2. So for each of these cases we want to figure out what the interval of existence is. So if you pointed out to yourself that tangent of t is actually a ratio of sine to cosine, and that cosine can become 0 as well, well, then we have all the trouble spots. So best thing to do is to go ahead and collect all of them. So first one, tangent of t, we write it explicitly sine over cosine. Whenever cosine becomes 0, we have an issue. You remember from your trigonometry, cosine becomes 0 at say 90 degrees, 270 degrees, and so on. Of course, we always deal with radians here. Pi over 2, 3 pi over 2, 5 over pi over 2, and so on. That is where this one has a problem. The other one has problems at 0, pi, 2 pi, 3 pi. All of these things, plus or minus, are the same problem spots. To keep track of things, the best thing to do is to draw a number line. So here I drew a number line. I listed all of these things. Well, not all of them, but so there is a minus pi over 2 and minus pi and so on. So you write as many of them as needed, or your patience allows. And then what does the theorem say? The theorem says very simply, where is this 1? Well, 1 is between 0 and pi over 2. Approximately pi over 2 is 1.5. So 1 is somewhere here. 1 is here. This is 1. Well, the theorem says we guarantee to you that the solution exists from 0 to pi over 2. So that's it. That the domain of existence for this thing is from 0 to pi over 2. So compared to all the problems that we have been doing so far that were really lengthy, these problems are very short and sweet. Of course, they are relying on a very significant, powerful theorem that we stated without proof, but well, every now and then things become easy. How about this one? Y1 is 5. Well, we're doing the same thing. 1 from 0 to pi over 2. It doesn't matter what the second number is. It doesn't matter how high the y is or how low it is. The answer is the same. 0 pi over 2. That's what we can guarantee based on this theorem. You know, sometimes the interval might become slightly bigger because of a certain rather miraculous thing that happens, but we cannot count on it, and we are not going to go on to that tangent. What we can easily say is the following: from 0 to pi over 2, it is guaranteed to exist. How about 5? Where is 5? Well, pi over 2 is about 1.5. This is 3 pi over 2 is about 4.5. 5 was going to land somewhere here. So if you start at 5, you're going to exist from 3 pi over 2 to and then your life is going to stop at 2 pi. What if you start at 10? Well, where is 10? 10 at 3 pi is 9 and some change, and this is passing that obviously, and 10 is going to be somewhere here. And then our solution is very easy. In this case, you start at 3 pi, and then you're going to cease to exist at 7 pi over 2, and so on. So again, short and sweet. But you might be wondering, well, this is a little bit too gimmicky. What is really going on? And to get a sense of this thing, again, a very good thing is to go to that very useful software we introduced to you a while back, the D-Field software, and look at the graphs of the solution and see what's going on. So again, we cannot solve this problem in the sense of actually finding what y is as a function of t. It's going to be too complicated, but we can surely look at it. So here we go to the D-Field software. So my equation was written as y. You remember there's little prime here, and everything is supposed to be pushed to the right hand side. So what did I have? I had y times tangent of t. So when the expression doesn't make sense, it becomes red. It means something has to be completed or corrected. Uh, and that's what we did. Now as soon as I put plus, it becomes red because it's saying, well, what about the rest of it? T minus 1 over sine of t. That's my equation. My independent variable is t. I don't have any parameters to worry about, and I just go with whatever window is giving me, and if I need to come back, I'll come back. So I ask it to graph the phase plane. So here's the phase plane. Rather hard to see what's going on because these arrows are flip-flopping in front of our eyes. So let's go ahead and try to look at some solutions. So if I click somewhere, it means I've chosen that as my uh, initial condition. Let's just pick some points, see what happens. Here is, you see, a solution starting from, looks like very high up, it comes down, lives here, and then it goes to infinity. Going to infinity meaning the solution has stopped. That was the interval of existence, like this thing, like a flower that bloomed for one day. That was it. That was its life. And here the software gives us some blurb about issues it might encounter, warnings, and what happened. What we are talking about mathematically about the existence also affects the software, because software is going to have a hard time dealing with what's going on at this situation. It's dealing with numbers that are getting out of hand, and it's going to warn us about that fact too. Now if you go ahead choose some other point, that's going to be another initial condition. So like this one, it starts at plus infinity here, and something is dragging it down to minus infinity. But the interval of existence is about the same, meaning if you draw a wall here and draw another wall here, from this wall to that other wall the solution exists. So what we have is this interval of existence. What's the beginning of it is 0. What do you think this point is? Again, think about it for a, well, I should give you just 1 second. Where is this point? Did you say pi over 2? Yes. That is where this vertical asymptote is, that pi over 2 we were talking about a second ago. This thing here. So we see some sort of a invisible wall at 0, another invisible wall at pi over 2, and when we are approaching these walls, what we see is the solution escaping to that. If you want to play more, be my guest, you see all of them. Now if you want to see this thing going toward that wall, you have to open the window and let this thing go higher, and when it goes higher it comes close to that wall. You notice some of them go up, some of them go down. That would be an interesting project to detect who goes up and who goes down. That's going to be an advanced problem. You notice what's happening. What if I go and choose an initial condition here? What happens here? You notice we are living on this side of this wall, on the right side of this wall. So let's draw some more of these things so that we can tell rather obviously. From 0 to pi over 2, it's like we have a tile and a bunch of creatures living between these two tiles, and then we have another wall from pi over 2 to where is this one? I'm sure everybody by now wised up. That is pi 3.14. That's the other wall. So things crowd around these walls. So if you come here and then so of course this is our pi, and this is, what is this one? that is 3 pi over 2. That's where the other wall is going to be. So if you want to see a specific case, we said that you can, let's erase all this clutter so that we see. When you say graph again, the clutter goes away. And then suppose you want to see just one of them. We said if you want to do one, you use keyboard input and then you enter your initial condition here. So for example, this in this problem we had y of, say, y of 5 is 7. Can I graph that? Let's come here. Where was this? Y of time was 5, y was 7. Before I start graphing is, would you guess what minor issue we are going to have with our picture? Do you remember anything about that setup that we have? Let's go ahead and see what happens. So solve it means use this as an initial condition and graph it. Well, maybe I should bring it up. Well, you might be asking, where is my point? T equal to 5. Well, this is t equal to 5. Our y is equal to 7. Where is that? Well, my window doesn't go as far as that. To see that, we need to correct our window, and so just to practice with the software itself. If you want to see 5, then open the window at least that far. So let's just be generous and so go as far as 10, and then so graph again, and then graph again. Now you see the little circle there. Perhaps on the monitor it might not be all that easily visible, but if you do it on your computer, you see it pinpoints your initial condition and tells you, well, that one starts somewhere here and ends up somewhere there, and the exact values for beginning and end are just the factors we found here. So that was nice and short. I hope some of you continue in the direction of mathematics and go ahead and try to learn the proof of this thing. Why is this powerful theorem true? Where does that come from? That's going to be, for example, in your real analysis class. Okay, we are going to have some other topics related to this existence interval to talk about, but let's postpone that to our next lecture. Until then, good luck and God bless.